That must go there. Yeah, that does. Gulliver's laws. That must go there. That must go there.
Royal Institution Christmas Lectures. Lecture 3, A Prodigious Leap.
Thank you very much. It was a great help. Last time we discussed the problem of Gulliver's rations, which the mathematicians of Lilliput felt would require 1,728 Lilliputian days' food to equal. And now we have made the calculation not according to geometry alone, but according to the correct experimental results which we have learned since the time of the Prince of Lilliput's scientific advisors about how mammals live. And there I've just repeated the calculation for those of you interested in having the right numbers. The food that a mammal requires per day goes about as his weight to the 0.73 power. Gulliver weighs 12 cubes, 12 to the third power, 1,728 as much as Lilliputian, by the statement of the work. His food, therefore, must be 12 cubed to the 0.73 power, which is the same as 12 to the 3 times 0.73 power, which is the same as 12 very closely to the 2.2 power. Notice that's a little bit more than 12 squared. Therefore, it's certainly more than 144. But it's much short of 12 cubed. And in fact, working that out on the slide rule or with a table of logarithms, you can easily find that it is about 230 Lilliputian rations. So he was overfed, if he were given 1728, by a factor of 8 times, about 7 or 8, which is pretty bad. On the other hand, if you think about the rations as having to be produced by the Lilliputians from agriculture, and according to Gulliver's account, the agriculture was very like the agriculture of England in those days, the Lilliputians would have to produce, you see, they eat not 1/1728 per man per day of what we eat, but only about 1/230th. So they eat per man per day, if they existed, about 7 times as much as we. Little animals are hungry, as I said. Lilliputians must be hungrier than people in order to support that heat loss. And this would imply that they have to grow their food 8 times as effectively on a given acre of land, a scaled acre with scaled grain growing in the scaled fields, as we have the description. And I don't think they could have done that. I doubt very much whether agriculture would be a possible way of life for an animal only as this size. So that shows one way, another way of seeing how deeply scale is built in to the structure of the world. Let us go on then and discuss not only energy and food as we have done, but now go on to something a little more complicated, perhaps the question of motion, especially the moving of animals. And I think you will find it interesting. Again, we can take our text from Gulliver himself, who writes, "The horses of the army and those of the royal stables, having been daily led before me, were no longer shy, but would come up to my very feet without starting. The riders would leap them over my hand as I held it on the ground. And one of the emperor's huntsmen, upon a large courser, took my foot, shoe and all, which was indeed a prodigious leap." That's the text for the day. Now, again, you will detect a certain criticism. I'm not sure it was a prodigious leap. We will see about that as time goes on. It was an interesting leap, and in following whether we are to admire it excessively or not, we will learn a great deal about the nature of real animals in the real world in terms of how large and how small they are. Let us look for a moment or two at real animals in our world. It's irresistible to try this antique device because it is so beautiful. It is rather well known. Here I have some strips on which are photographs of running and leaping animals in successive positions, one after the other. Notice the greyhound running, made and demonstrated here at the Royal Institution nearly 90 years ago by Mr. Edward Muybridge, who was the first man ever to take good photographs of animals in motion in sequence to produce the illusion of motion by the familiar principle of the motion picture screen and the television screen. We can do this by still older methods using his photographs. The machine is even older, I believe, but his photographs are in it now. And we can, if you like, look at this zoetrope and watch a horse leaping, a real horse leaping. I think you can see it. Soon the obstacle will come around. And there is the horse in these successive photographs, one after another. They were taken not in a motion picture camera, spooling the film through exposure by exposure, but by the straightforward and heroic device of having a dozen cameras, one after another, arranged in a line. And the horse ran past the whole line of cameras. As he ran, his foot touched a fine wire. Pulling that wire, he operated the shutter of each camera in turn. So the successive pictures came out, not on a long strip of movie film, but as 12 or 24 successive photographs. Now look at them rapidly, one after another. You have this nice illusion of motion. And Muybridge did this in order to settle a great wager, again, made by some California millionaires in those days, as to whether a running animal ever achieved a state for an instant in which all 4 feet were off the ground. Of course, the answer is yes, and it was first established then at that time. Let us look a little bit to discuss the question of jumping. Let us look at some films with modern motion picture technique of animals jumping. First of all, we will get to see a horse jumping in slow motion. This is the horse of Miss Cokes, winning an Olympic silver medal for her jumps. Rather beautiful action of the animal. Watch the animal going over one of these obstacles. Obstacles are just short of 5 feet high. The animal, you see, lifts himself just over it, picking his feet up carefully as he goes past the edge. And another one still. Quite beautiful work. Now, if an animal jumps over a 5-foot set of bars, are we really to give a large animal credit for jumping 5 feet high in the air? Do you think that is really a 5-foot high jump? I don't think it can be, because after all, he doesn't start from flat. A horse is already 5 feet high. What would be the right way to count the height of the jump? Let us look, for example, at a smaller animal, where it makes more difference. We can see the jumping of a smaller and less well-known animal, perhaps, in this next film, which is another California product, more up-to-date, I think. And the California product is, here it is, the jumping frogs in the famous contest in the California mountains. Watch him again and try to get an estimate of how high. There, oh, splendid. Now you see, the frog jumps many times his height, but of course the absolute height, the actual height he jumps, is about 2 feet. Let us watch the best of all, most subtle of all jumpers anyhow, the most understanding of jumpers, a man making an Olympic high jump. I think we will soon see the film, I'd like to see it twice, of Dick Fosbury, the American high jumper, winning the gold medal at the recent Olympics, jumping over a bar 7 feet 4 inches. Watch him go, again in slow motion. Pay particular attention to how his body goes over the bar. Look at that. Now I wonder if we can see that again. I hope we can. Now, did you see what happens when he goes over the bar? Does he retain? You see, if I were to think very simple-mindedly of how to jump over a bar, I would imagine you just run along and you jump and you soar over the bar like that. Not that way at all. How does he do it? You all saw that, I think. He jumps over the bar, and when he is above the bar, he's by no means twice as high at all points as he was before. He hasn't jumped over his head. He's a 6-foot high man. Watch him go. There he starts off, Mr. Fosbury, a splendid high jumper, the world's best. He approaches the bar and dives over it, head first, upside down, looking upward, thank you, and has really done us a splendid job of jumping. Now notice, that brings out the point I wanted to make. We count, for the purposes of athletic contests, we count the height as the height of the obstacle over which the animal jumps. But from the physical point of view, that isn't how high he's really moved himself. That's simply a convenient thing to measure, and therefore that's a very reasonable thing to record. But in fact, Mr. Fosbury started off, if you like, on the average 3 feet high or so, did he not? And he therefore raised himself about 3 or 4 feet, because when he goes over the bar, he's only, so to speak, 6 inches high, the thickness of his body, and he's raised himself from being 3 feet high on the average, the center of mass, if you like, until the center of mass has come here and he's now flat, maybe 3 feet or at the most 4, not more than that. On the other hand, the frog raised his center of mass from being 1 inch or so high to being a couple of feet high. So the frog has jumped about 2 feet, and Mr. Fosbury about 4 feet, and the horse about 3 or 4 feet. I would suggest that all of these jumps are very similar for animals of such extraordinarily different proportions and size. And in fact, that leads us to our conclusion we'll come to in a moment. But before we do that, I think we should look at another animal jumping, and I think we have a couple of volunteer jumpers. And I want you to pay special attention to this notion that the height of a jump should be counted more physically by how high the mass is raised. So we have given our jumpers lamps to mark their centers of mass pretty well. And we'll let them jump in the dark, so all you will see will be the marking lamps, and you will therefore watch these two very excellent jumping beasts of different size will jump for us, and we will have why don't you jump once in the daylight, in the house lights, so we can see how it looks, just once or twice to show everybody what it looked like. Go ahead. Very good. Enough. Don't tire yourself out for the real thing. Now put your lamps on. And now watch what you will see is the lamp at the center of the buoy. Now if we can have the house lights down, please. We'll see only the lamp at the center of the jumper and a fixed scale of lamps 1 foot apart, which will mark the height of the jump. All right, jump at will. Very good. Now you see, that is a good deal more like a frog jumping than it is like what we think of as that. Thank you very much. We can have lights again. I think that those jumps, let's give these athletes a hand. These jumps are a foot or 1.5 feet without special athletic equipment, without any run-up and so on. And you see, when we notice the actual change in the position of the bulk, it brings them closer together. The small animal no longer appears to be jumping so much differently from the large. And in fact, all animals, as far as I can tell, who jump at all, I don't suppose a boa constrictor would be able to make much of a jump, but all animals who jump at all reasonably well, and I think probably even tiny ones like fleas and grasshoppers, I haven't tried very much, jump somewhere a couple of feet. Maybe 1 foot, maybe 3 feet, but nothing much different. So a remarkable result occurs. Nearly all animals jump about the same distance. There is an exception or two. There are some splendid jumpers, like the kangaroos, who are specially adapted for jumping with huge hind legs and tail propulsion, jet propulsion perhaps, at least reaction propulsion. And there's also a beautiful antelope in the eastern African plains called the impala. I think if we're lucky, we might be able to see very briefly a slow motion picture of this excellent jumper, who probably jumps 1.5 times or possibly even twice as high. There he goes. Isn't that a soaring jump? Magnificent. I'm glad we don't compete against impalas in the Olympics. And these animals jump extraordinarily high, much higher than the others, but when I say much, I only mean twice as high. So even these exceptional cases are not that different. Can you think of a man who has equipped himself in such a way, so to speak, changed his anatomy, changed his shape, to allow himself to jump much higher than the champion high jumper, Mr. Fosbury? Yes?
Pole vault.
Pole vaulting, exactly. What is the pole vault, after all, but a man who's developed a very strong, long limb, which he can push down and soar up to the top of, and a good pole vaulter can go up over 18 feet. But only at the price of giving himself a large piece of pole to work with, And by the way, I don't think you'd do that if that pole had to be attached to him and nourished by his food. In fact, he's got to have a very light, strong bamboo or nowadays laminated plastic and fiberglass pole. And that is a typical example of how you can get around the scaling laws, but you can never actually break them. You bend them, you evade them, but they still apply. To show that it is not only a question of the flesh and bone animals, we have produced here a series of interesting scaled jumping machines. Very simple they are, but they are, if you like, machines which jump. And they have bases, and they're all very prettily scaled so that each has its size. The scale, as I think you can see, is 2 to 1 in each step. This one is just half the size of the large one, and the small one is again just half the size in all parts of the middle-sized one, so they stand in the ratio of 1 to 1/2 to 1/4 in linear dimensions, which I could call L, my usual L for length. Now let us see how they jump. They have been adjusted so that all the dimensions are the same. That's to say, not only are the lengths the same, and you notice I have the same difficulty in setting them as one has always in setting a mouse trap, and the same fear of catching my fingers in the jaw. Escaped that time. The dimensions of the wires are twice as great. The dimensions of the power is adjusted to be proportional in the rubber bands which power them. You see what happens? The rubber bands will sharply contract. The legs of the jumping machine will press against the base. And the machine will hurl himself spectacularly into the air. Or anyway, pretty spectacularly. And let's see how he jumps. Of course, we can't compare the height of his jump to that of a human or a horse because it's made of quite different materials. What we want to do is compare the various sizes of jumpers. So here we have it. It's a nice jump. I hope you noticed about how high that one went. That was the largest scale one. And now we take a middle-sized one. Let us try him. Ready? About the same height. Not much different. That's quite interesting. And of course that bears out what we said, that they will in fact jump about the same height. Now it's worthwhile weighing these two to see if we may, what their weights are, just to check that the scaling has been done quite well. Will someone help me? Thank you.
93 grams.
93 grams, very good. Let's try the middle-sized one. Let us first ask, how much should it weigh? If it's 1/2 the dimensions, 1/2 this way, 1/2 that way, and 1/2 this way, it should weigh about 1/2 times 1/2 times 1/2, or 1/8, which would be 1/8 of 93 is about what? 1/8 of 88 is 11. 1/8 of 93 must be about 11.5, say 11.5 or 12 grams. What do we get?
12.5.
12.5, very close. You recognize that to make these machines is not simple. These machines were designed to be scaled by an undergraduate student of mine who did it as part of his thesis at MIT, and they're beautifully made here in the Royal Institution by Mr. Bruce Morris. And here we have the small fellow, and let us try how he works. Again, we place him on the base, and we pin him down. And try the jump. Unmistakably a poor jump. What is wrong? What could be wrong, do you think? Anybody?
Weighs too much.
He probably weighs too much. Let's weigh him. How much should he weigh? Let's discuss. He should weigh about 1/8 of about 12 grams. That's about 1.5 grams, or a little less. What does he weigh? 3 grams. He's overweight. We shall put him on a severe diet in the morning. And because he's overweight, he couldn't jump so much. We produced him this way. It's just the way it came as we went into the shop. Why do you think he's overweight? It's very difficult to scale down a piece of apparatus. Consider, for example, even the weight of the paint is not proportioned. You can't make a thin layer of paint sufficiently thin, and the solder joints and everything else contribute until we are no longer quite sure of how to make a very small object weigh in scale. If you sometimes buy model railroad locomotives and the like, you will find, if you weigh them, they're enormously heavier than their scale weight should be. Often 10 and 20 times heavier than they ought to be on scale. They're solid, full of machinery, and not full of the airy cabin of the locomotive engineer. So this is their trouble. Let's getting along. I think there is a fairly clear lesson in this, the lesson of scaling of devices, but let us try to get the theory a little straight so we understand why we can see at once, from arguments of energy alone, that all animals, if they were perfectly similar, and in the simple theory of jumping, would jump about the same distance. And I think it's quite easy to see how that goes. What is the requirement to jump? You must lift your weight a certain distance. So the energy needed to jump, the energy of a jump, is proportional to your weight, which is the cube of the dimension, any dimension, say L cubed, the length, the height, we're all similar, so any dimension would work for the cube, times the height of the jump. As you know, the energy that you do against gravity is the amount of weight you lift times the distance you lift it. And the energy available is the amount of energy in the muscles. The muscles have a force which is like their area, like the rubber bands of our model. And they have a reach. They move through a distance. The long-legged beast through a large distance, the short-legged one through a small distance, like L. And the energy available, therefore, is like L cubed. This is equal to L cubed. Now notice, this depends on the third power of L, and this depends on the third power of L. So there are two cubic curves going up together. Whatever ratio they have at one size, they will have the same ratio at every other size. Therefore, the height of the jump, which is the only number remaining, does not depend upon the size of the animal, which is what we have, approximately. Though we've considered animals very different in shape and size, we found that their jumping distances were quite similar. It's a very curious result, which was borne out by our test with the jumping machines. And that seems to work reasonably well. Now, I think that the most interesting thing to examine now will be another kind of propulsion. The jumping is perhaps a little special as a means of getting about, but it's an interesting one, related directly to what Gulliver talked about. You see what our conclusion is now. Gulliver's horse had no trouble at all in jumping over his shoe. In fact, Gulliver's horse should have been able to jump more or less like a frog, or somewhat better than a frog, a couple of feet high. He could have jumped over Gulliver's head while Gulliver was sitting down very nearly. So that in fact it was not a prodigious leap, but a very modest jump for an animal made like a horse, as active as a horse, and 6 or 7 inches high. That's our conclusion. In fact, if any of you keep small animals, mice, hamsters, even squirrels, I think you will notice that they are splendid, prodigious leapers. They can jump several feet, which is a good many times the size of the animal, and you don't see that happening with any larger animals in the world. And this, of course, is exactly what we expect, since the size of the jump does not depend upon the size of the animal. The changing weight just compensates for the loss of strength in such a way that the jump is always the same. That's the conclusion of this particular examination. Now, let us look a little bit at walking, which is a more normal kind of propulsion, and see how that goes. Let me do this rather quickly, and we'll watch how the walking proceeds. Here we have a walking device, just to remind you of how something walks. This is an artificial limb, and we've loaded it a little bit to make it look a little more real. And now, if I walk, I make the limb swing, but I don't press hard. That's what a walking gait is. I just let the leg fall back into place, so to speak, without any special drive. That's not at all the same as running, and we'll talk about running later. But I think if you'll think it to yourself when you're walking or running next, try to see how it is you're moving. It's a complicated action, but the essential feature is that you move forward and fall back, move forward, and fall back in just that fashion. Now thank you, Bill, that gives rise to the notion that the principal determiner of the speed of walking is not at all as one might think, the complicated mechanics of the muscles and the bones. In fact, it is very simple. The main determiner, perhaps not the only thing because we're trying to simplify a rather complicated kind of motion, the main determiner is the swing as the swing of a pendulum, a very straightforward matter. And that swing, as you know with a pendulum, takes longer the bigger the pendulum length. The greater the pendulum length, the more the swing of the pendulum. Therefore, we can say that the time for the swing is proportional to the square root of the length of the pendulum. In this case, the length of a characteristic bone or characteristic typical size of the animal, any size you want to choose, any dimension, let's say his leg length. I can write that, of course, that's the same as the fractional exponent L to the 1/2. If you prefer this notation, why, very good. Now then, notice what that says. That says the time for a pace is longer the bigger the animal. Let us try that a little bit to see if there is any reality in that picture. I don't think we need those. Well, all right. All right, we shall look at them then very quickly. Just to remind you what a pendulum looks like. Here's a long pendulum. And here a short one. Notice many more beats in the same interval of time. That's quite familiar. And if we were to measure it, you would find it would go very tolerably like the square root of L. Thank you, Bill. Now let us do that for a few animals to see what they look like. And their appearance is as follows. Can we have again some of our boy walking schemes? Now, the idea is to walk, Martin, and not to hurry. You're sauntering down past the park in the summertime and not very busy. You're not late for school and just walking along. Go ahead and I'll give a start to Bill to start. You just walk along peacefully. And start. 1, 4, 5, 6, 7, 8, 9, 10. What did we get? 6 seconds. Well, that seems pretty good. And 6 seconds for a boy walk. Now, let us try a smaller animal. I think we have a performer here again, Tessa, a member of the Coates family, as I recall. This is a complete Coates performance here. And let's see how Tessa walks. Let's start her off, and I'll try to count. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About like that. 3 seconds. Very interesting. And now you see quite well that the smaller animal has taken much less time for a pace. Let us look now at a larger animal. Again, we have our same problem. Hard to bring in the large animal, but not so difficult with the splendid effect of film. So let us look in a film at a large animal and try again to count with me her paces once I begin. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Splendid. 8.5 seconds. There you are. There's certainly no question about the time increasing from 3 seconds to 8.5 seconds for 10 paces. That's a factor of about 2.4 or so. If I were to square that, I would get about 6 or 8, and it seems reasonable. The dog's leg height is about a foot or a little more than a foot, and the giraffe's leg height is about 6 or 7 times that, 6 or 7 feet, and that comes tolerably close to the square root of L. But notice something. Does that mean that a giraffe walks slower? Her paces are slower. But does she walk slower than Tessa? Who would win in a race? A walking race. What do you think? The giraffe, yes. Why? The paces are slower, but what? Everybody. It takes longer per pace. That's exactly right. The speed, after all, is found this way. The speed is the distance over the time. But the distance per step surely is proportional to the size of the animal's leg. He makes a long step. So proportional to L divided by the time, which goes like L to the 1/2, the overall effect then is like L to the 1/2, and the speed is greater, the walking speed, for the bigger animal. I recommend you to try that on boys of different heights, on girls, on horses, men, women, dogs, squirrels, anything you can find. See if this rule really works for walking. I think that it does. Now, walking, of course, is not the only kind of locomotion either, and I think we should discuss a little bit the problem of running, which is a still more exciting kind of activity. Running animals are an interesting proposition, and they teach us a great deal about the nature of scaling and the nature of these problems. Again, with a rather surprising result. And I think the surprise of this result is the main point that I want to bring forward. In order to discuss a theory of running, we must first, well, let us first take a look at what a running operation is like. And I think this is, I can't do this very well, it's really quite difficult, but I think I can suggest to everyone so that with our experience you can understand what is involved. In walking, I did this sort of thing, and I let the limb fall back in a smooth way. But in running, you press both forward and backward, forward and backward, forward and backward. And the speed at which you go does not depend primarily upon the size, but upon how rapidly you can make your limbs move, reversing. You've got to speed them up and then make them go backwards, speed them up and make them go backwards, speed them up and make them go backwards, repeatedly, over and over again. Of course, running is very much more work, thank you, than walking, and the nature of the energy use in running is quite different. So let us discuss a little bit the theory of running from this point of view. I'm going to argue, and this will require a special set of measurements, but we can be pretty sure of it, that air drag is not very important for the runner. Indeed, that is quite true. Animals generally don't get up to high speeds, so that streamlining, for example, is not something you observe in walking or running animals. Where do you see streamlining in the animal world most neatly? Yes, in fishes. Fishes are immersed in a much denser medium, and it is important for them to reduce the drag of the water. That is the principal use of energy in their locomotion. It is not true for animals in the air. The air drag is not as important as the interaction with the surface and as the speeding back and forth of their limbs as they move. Let us look for a couple of pictures to remind us what running animals look like. I use this picture particularly to remind you that the data on fast-running animals is hard to obtain. If you tried chasing a giraffe in a Land Rover, you're not so sure. Is he really doing his best? And it's really not a very good way to make experiments. We have, however, very good statistics and very good experiments on animals of certain kinds. For example, the greyhound, the horse, and the man. I leave it to the audience to decide, especially here in Britain, why that is true. But we have that. So here's this excellent animal. Here's an animal of the sort that you see out of the careening windscreen of a Land Rover. There's a running away buffalo. If he turns around, you turn around too. So against the East African, you see the savanna in the background, the East African plains. Thank you. Now, such animals are difficult to get data about. Therefore, our best data, our best numbers really come from the racing domestic animals where we can try it over and over again, where we have skilled trainers and careful measurements, and things are really believable. When you come to wild animals, how fast they go, it's an endless source of excellent discussion and arguments. And indeed, for all I can find, no one has yet given me any good measurements. I've not been able to find them in quite a lot of work, looking for the speed of running of small animals, really small animals, mice, rabbits, and so on. And I urge any of you who are here, who are good managers of small animals and have friends among small animals, to try them out. Get them so they like to race. I don't recommend that you whip them, but get them so they like to race, lead them along, or do something of the sort, and measure the speeds of these animals, because I think this will very nicely help us in our work. You'll see what happens as we go along. But we don't have that at the moment. We have a good deal of information. I should try to write it down. But mind you, I prefer to take with a grain of salt yet, not quite established, all the statements about wild animals and animals other than these well-raced domesticated ones, because unless you have quite a few animals to try and good circumstances for trying it, you never can be quite sure that the numbers are really reliable. I think that's a fair statement, and you understand how hard it is to make measurements. Let us then go ahead to look a little bit at the theory of running under my assumption, which is, I think, not a bad one, which further measurements would support, that the air drag is not important, and the principal loss of energy is to this terrible business of putting energy into the limb to make it move rapidly, then taking it out again, doing work to do that, then putting it back into the limb to make it move rapidly the other direction, taking it out again, and so on, back and forth, back and forth. That's where the energy goes in running. And it's quite clear that that's the case. Let us see what that leads to as a result for the motion, for the running motion, the running speed of animals. We saw how the walking speed would go. Both the walking speed and the pace speed. Interesting result. The time per pace gets longer as the animal gets bigger, but the speed of walking gets greater as the animal gets bigger, and that's not a result I think we would offhand have got. But we see how we cannot get around it, and it fits pretty well to the facts. Let us see how much work we do in moving our limbs. Well, the load again goes like the cube of a dimension, the cube of the length of the leg, the length of the arm, the length of the forepaw, whatever length you want. Because remember, our calculations are always made for animals that we imagine to be exactly similar, just as Gulliver, Lilliputians, and Brobdingnagians were exactly similar, except in size. In the real world, we don't find that. So we can't expect precise agreement. We expect just a rough indication of how things go, since no two animals in the real world are really built just the same shape, as you might for yourself examine. Now, that's the load. On the other hand, and therefore the mass, you see, the time in which we have to take this energy out of the limb and back again is the time of a step, and that's the distance in a step divided by the speed of the runner. The distance divided by the velocity. You remember that the distance is velocity times time, so that would check out. Time is distance over velocity. Now let me calculate the kinetic energy. I'm sure that the physics students anyhow will know that the kinetic energy is proportional to the mass times the square of the velocity. Since I have a proportionality sign, I don't have to remember that troublesome 1/2, which you might have to remember for examination purposes. And this is, of course, just the m is like the volume and thus the weight. The m is the load, L cubed. The velocity is v squared. That's the, sorry, yes, that's correct. And I have to divide this by the time. The kinetic energy per unit time is the power. Kinetic energy per unit time is the power that I must develop in running. That's what our problem is. How many kilowatts do I use in running? This is the kinetic energy, proportional to that. And the time is L over V. And so you see that the kinetic energy is proportional to, kinetic energy per unit time is proportional to L squared. That is the result with the V's, L squared V, if you like. That tells me how much power I am required to run with. But how much power do I have available? And that's an interesting thing to ask. This is the required power. Let me write that down, erasing this part, and simply store the result up at the top. Power required was proportional to L squared V. Power available, well, it's the energy available divided by the time. The energy available in a short sprint, anyhow, depends on the bulk of my muscle. Again, it's the L squared, the strength of the muscle, times the L, the distance the muscle will move. Or if you like, it's simply the weight of the muscle, which stores up its own oxygen and contains what is necessary for a sprint. Would not be true for a distance runner, but for a sprint runner, which we're describing. So again, I have L cubed for the energy store, and the time it must be made available is the time of the step, L over V, and that is the same as L squared V, and these two are the same. And I therefore come to the strange conclusion that the running speed of a fast burst of speed from any animal, at least of mammalian sort, it doesn't vary too much in chemistry, must be the same for all sizes, which is a quite striking result, like the jumper. Now, do you believe that result? I found it very surprising, but looking at the data, it comes out really pretty well. Again, the animal's not exactly similar, so we can expect small variations. What we're looking for is a variation in running speed that is quite small compared to the variation in the size of the animals. Then we know that this is, to some degree, correct. I'll give you a few numbers, You'll see how it works. These are all sprint speeds. First, the well-known four-legged beasts, the racehorse, the greyhound, and the whippet. The racehorse I have here in miles per hour, 40 miles in a sprint, 40 miles per hour. The greyhound, 36, and the whippet, a much smaller animal, 33. So while there's certainly a difference, it is not an enormous difference. And these races are even these are not the maximum burst of speed, I think, quite. They're the speeds over a distance they allow for starting and stopping, so they're not perhaps absolutely correct. A man cannot do as well. A man can only go about 25 miles an hour. On the other hand, allowing for the difficulty of measuring wild animals, I'll write down a few others. A red fox, a beast of only about 6 or 8 pounds, can go about 45 miles an hour. This experiment, I understand, is carried out very frequently in Britain. The racehorse versus the... And a bison, who is related to that African buffalo we saw, can go about 34 miles an hour. So you see this enormous range of different animals, and there's not as much as a factor of 2 between them, and indeed, probably excluding man, they're even closer than that. There's one rather exceptional case. I'm a trifle suspicious, but it's probably true. There's a beautiful animal called the cheetah. Have any of you ever heard of a cheetah? Yes. What sort of an animal is he?
Leopard.
A cat. And do you know what they're used for? They're actually somewhat domesticated in the Sudan and Somali and Ethiopia. Yes.
Hunting.
They're hunting animals. They hunt with a fierce burst of speed, but they can't go very long. And they're supposed to be able to go 65 miles an hour. Now, I've not seen one, and I'm not sure, but I just quote the numbers as they came to me. It might be true. I hope someday somebody will give us really secure information, films and measurements and many trials to tell us whether a cheetah really can go that fast. But notice, even then, the differences are not very great, and I think it's quite striking that this can be so similar from size to size as we have it. Now, if you work out the duration, then of course there is a difference. The time is different, and for short bursts, of course, the large animals can run down the smaller ones in general. But if you don't make it a running spurt, but make it an all-day long sort of affair, how much distance can an animal travel in a day? It turns out, again, there's surprisingly little difference among the sizes of animals. You can work that out, if you like, using the all-day energy supply as equivalent to the food required. That is, going as weight to the 0.73 power instead of to the weight as I do for spurts. And then you will find that there's a very small dependence indeed, very slow, of distance covered in a day against size of animals. We might show you how this is done for small animals anyhow. Here is an activity wheel, so-called, a balanced wheel, simply a light wheel in which a mouse can be placed, or any small animal, and he can then be induced. In fact, he likes very much to do it. It's hard to stop them. I'm sure Beatrice, who's not a he but a she, will show us how she races in the activity wheel, so she can go a long distance and not get away from us. And by counting the number of turns, we can, there she goes. And while this does not seem like very much, I am amazed to find that in the recordings, not perhaps quite of Beatrice, but in other records, these small animals, mice, kangaroo mice, and the like, have gone 30 miles or 35 miles perfectly safe and healthy in a day's journey. A man can go perhaps 80 or 100. That's all. And the difference is only a factor of 2. Again, the same thing happens. The distance you can travel is more or less independent of the speed, which means, of course, that the Lilliputians could go splendidly at their walking pace. Well, the window has come open too. I think we'll close you up and put you away, Beatrice, if we may. The Lilliputians, if this is correct, I compute could have walked a young Lilliputian in good condition could walk about 300 Lilliputian miles. Whereas a young Brobdingnagian in good condition could walk only about 8 or 10 Brobdingnagian miles in 24 hours. So you see how much more free to move and active in their scale small animals are. Or another way of putting it is, the freedom, the range of an animal is not much dependent on his size. I think an extremely interesting result. Now the last point that I want to touch is flight. And I think we will just not, I think we'll suppress those gliders. Yes, I think we might have a weighing machine now. That would be nice. And let you throw the boomerang and I'll be satisfied. Here we have a familiar object, a table tennis ball, which I take to be a typical example of something whose flight through the air is obviously strongly affected by the resistance of the air. Whoever has played table tennis knows that very well. That table tennis ball is a few square inches in area. Just, oh, thank you. And weighs, what does it weigh?
2 grams.
Weighs 2 grams. As long as you have grams per square inch or grams, a few grams in many square centimeters, you can be sure that the air resistance is most important. Will you show us your small cross device, Bill, and let's weigh it just to get the idea.
This weighs 7 grams.
It weighs 7 grams, and it has an area which we have measured before. It turns out that the loading on that is about 1 ounce of 1 ounce load, a few tens of grams, in a square foot of area. Would you operate it? Thank you very much. Now, it's perfectly plain that sufficiently small loading, that is sufficiently small weight per unit area, like the ping pong ball and the boomerang, will give motion in the air affected not only by gravity, which affects everything, but strongly by the air itself. That's clearly the lesson of this remark. Now, we know of many animals, including man aided by machine, or as we will see, almost unaided by machine next time. Many animals are capable of motion through the air. And what we have to take into account, however, now we must take into account the effect of the air on moving things. And I want to do that to come out with some very interesting results concerning flying animals. And then next time we'll be able to apply this not only to animals that fly, that's to say birds, bats, squirrels, pterodactyls, anything else you have in mind, but also to machines, man-made machines, which also can fly. In fact, here we see a rather nice slide, which is wing loading. On the left, the pounds per square foot of wing loading against the weight of an airplane, against the weight of the flying vehicle. I think you can see that. And notice the entries: lark, black-headed gull, pigeon, herring gull, buzzard, vulture. The weights are going up as you go to the right, and the wing loading is going up. The biggest wing loading of any bird at the far right there that is listed among these dozens, and I don't think it's greater for a condor or an albatross. The biggest birds weigh 20 to 30 pounds, and their area is some tens of square feet. They load up, therefore, to a pound or 2 per square foot. Beyond that, we see no flying animals. Now, that's an extremely, thank you, that's an extremely interesting result. Now, the nature of this result can be seen if we make a theory a little more in detail. The vulture at about a pound per square foot, the boomerang at a much smaller value, say an ounce per square foot. You see how much more flyable, and now think of the small birds that fly. The Wright Flyer, the original airplane, about a pound and a half per square foot, and a light airplane of today about 10 times as much, nearly 12 pounds per square foot. A VC-10 takes off with maximum loading at 110 pounds per square foot. I leave it to you to think how it is possible to fly when you're so heavy as a VC-10 per square foot of wing. What does it? Partly, of course, it's the cunning shape that the engineers have designed in, the enormously clever streamlining. But that's not all of it. What is the main thing?
It's the vacuum in the wing.
Oh, well, all of the flying things have vacuum in the wing, without exception. Above the wing, there's low pressure. It's the air on the bottom and the low pressure on the top makes it lift. But that's true for the ping pong ball as well. But the difference between that and this, yes? What do you think?
Drag on the wing. The drag on the wing.
Yes, well, what the difference between the VC-10 and the Wright Flyer is very straightforward. Enormous power. Huge engines. We'll see how that goes. In fact, we can do that in the following straightforward way. The airplane must, to sustain its weight, it must have a lift which is about equal to the weight. And that is proportional to the area of the wings. I think you would believe that. And now, for the moment, let us take it proportional to the square of the velocity. The faster it goes, the more lift. We can show that presently in a rough way, but let us not worry about the square. That is true for the range of most flying objects that we are talking about. Therefore, the weight can go like AV squared. And therefore, if I solve this, I have that V goes like W over A, and I'll take a square root to make that equation true. Now, the power required. What is the power required? Power required is the force, which is the drag, which is like the lift. They must be related. The design of the wing will tell us how much of what fraction one is of the other, but they must be proportional. And that must be like the weight, that's the force, times the velocity. But the velocity we know, it's like the square root of the weight over the area. So the power required for flight is proportional to the weight times the square root of the wing loading, the weight divided by the area. And you see, as the weight gets bigger and bigger, the power required becomes very great indeed. That is the nature of aircraft, of manned flight. That is the clear answer why sufficiently large animals simply cannot fly without the mechanical aids that men have. For example, if I ask what power must I develop per unit weight, the best an animal can do is keep that about constant. Then power divided by weight goes like wing loading. As the wing loading gets bigger and bigger, the animal has a harder and harder time to fly. Therefore, only light animals can fly, and large animals can never fly. They don't have the requisite power. The power has come in only when men were able to make gasoline engines and other forms of power which could make them fly. There is a marginal place, which we'll discuss next time, where men may be able to fly, just barely to fly, with the aid of their muscles alone. But let us look a little bit at what experiment you would have to do if you were to try to check this V squared in the lift formula. Can we have this bit? We may just manage it. Here is a device, a small wing, model wing mounted, pulling a thread which works a scale on a dial to show the amount of drag and thus the amount of lift. Here is a fan, a small fan which can turn very easily, and as it turns is counted, and it turns so lightly that it shows the speed of the air going through it. We will turn on the machine and vary the speed of the air. You'll hear a great speed change in the motor, but that's not the same as the speed of the air. We have to measure the speed here, and as the speed increases, so you will notice the press on the wing increase. We will probably not have time to produce the numbers, but just this setup, carefully done in all scales, as you know, in wind tunnel 50 years, has produced the valuable result that the lift is proportional in these ranges of size to the square of the velocity. Okay, Bill, let's try it on. I watch the velocity by measuring this. I'll give you a time. This counts how many times it goes around. It's building up to speed. Notice the lift now. All right, start. Stop.
5 seconds.
5 seconds. Very good. Let's speed it up, and you will hear the motor turning faster. Notice. Start. Stop.
1.5 seconds.
1.5 seconds. You notice about 3 times the velocity, or 4, and much more than 4 times the lift. In fact, we're probably in the range where the lift is not going up any faster than the 1.5 power of the speed. Well, next time we'll be able to discuss man's machines for flying. In other words, the news from Lilliput and Brobdingnag since they began the technological development that we have had since the 18th century.